Hello, good people. Welcome to video one of section 6.1 and 6.2. We're going to combine these two because they kind of go hand in hand. 6.1 tells us what is it we actually find when we look for the area under the curve with a definite integral. And then number two says what happens when we can't find the area under the curve because our function is not a geometrically nice shape, if you will. But let's take a look at this example, situation one, and see if we can figure things out kind of organically. The particle P moves along a straight path with a constant velocity of 2 feet per second. So I need you to know that what we're looking at is not the path. This is not the path of the particle. This is the velocity of the particle. So the velocity doesn't change. From time 0 to time 2, the velocity is 2 feet per second. The graph of v of t, v sub p of t, is given above. So this is the velocity of particle P at any time t. What is the total distance of the particle traveled from time 0 to time 2? Okay, so let's think about how we usually find distance. If you remember back, distance is really just rate times time. So if I'm looking for the total distance, I need to know what's the rate of change that I'm moving at. Well, the rate of change would be the velocity. And then I need to know the amount of time that's expired in this situation. So in this case, that would be 2 minus 0, right? Because it said from time 0 to time 2, there's a difference of 2 seconds. And so if I multiply those two things, then I will get the distance. The velocity, it doesn't change. It's always 2 feet per second. Times the time, well, the window of time was from 0 to 2, so that's 2 seconds. This is seconds as well. And if you look carefully and do some unit analysis, if I'm multiplying this unit times this unit, here I'm dividing by seconds. Here I'm multiplying by seconds. So the seconds are going to go away, and you're left with feet. And 2 times 2, well, that would be 4. That is the total distance that this particle traveled between time 0 and time 2, a total of 4 feet. Now, if I go back to the picture, how could we have figured that out? By looking at the picture instead of doing our calculation on the side. And so we look at this and we realize, oh, the distance that I'm looking for is really just the area under this curve from time 0 to time 2. So in a very real sense, when we do the integral from 0 to 2 of the velocity of particle P in terms of t, this definite integral, which creates this area under the curve, is really finding for us the distance that the particle has traveled. So think about that. We're using velocity, taking the integral, and we're getting the distance traveled. We are accumulating change, we're adding change from time 0 to time 2, and all of this change that we're adding is adding up to the distance traveled. That's it. And so our goal here in 6.1 and 6.2 is to kind of play with this idea that finding the area under the curve really just means we're accumulating the change of whatever function we're given. In this case, we were given the velocity function. Or I guess I should do it in this color since I did it in orange. We were given that velocity function, and we're able to find an exact, not only are we able to find the exact area under the curve and definite integral value, we're also able to interpret what it means. So then I come to situation number 2. Situation number 2 says there's another particle, a particle called Q. It's also moving along a straight path. Remember, this is not the graph of the path. This is the graph of the velocity. Its velocity is increasing as it moves. The graph VQ of t is given above. What is the total distance the particle traveled from 0 to 2 seconds? Well, when I look at this, if I try to do the same thing and find the area under the curve, I run into an issue because I don't have a nice geometric shape whose area I can figure out, right? This is now has a curvy side. But the idea is still the same, which is to find the distance, we multiply v of t times time. Because v of t, which we'll say is measured in feet per second, times time, which is measured in seconds, will produce the unit of distance, which in this case might be feet. And so I run into an issue that I can't find the area of the curve, so I can't find the exact distance that it traveled. However, 6.1 and 6.2 are going to help us with situations like this. What if we broke this shaded region into maybe not the exact thing, but an approximated shape? For example, what if I connect these 2 points with a straight line, we'll say, and if I find the area of this purple shape, that area is more than the area that I want in blue. However, I can at least get an upper bound, right? I can get it can't go above this value because I can see that the shaded region is under that value. And so for that, we're going to say that the total distance traveled from time 0 to time 2, even though I can't find the actual distance, I can say that that distance is less than the area of this shape. Now, what shape is it? Well, some people, again, will break this up into a rectangle down here and a triangle. I'm just going to treat it as a trapezoid that's kind of on its side. So this would be base 1, this would be base 2, and then this, ironically, would be the height, even though it's not up and down. But if you turn your head like 90 degrees, you can see, oh, this is just a sideways trapezoid. And the area of a trapezoid is 1/2 the height, which is 2, times base 1 plus base 2. Base 1 has a unit of 1. Base 2 has a unit of 3. And when I do this business, I get that this equals 4. So the actual distance that this particle Q went, even though I don't know what it is, I can definitely say it's less than 4 because the shaded region is inside of the shape. And what's coming up in the subsequent videos is using some estimation tools. Some of them are trapezoids, like what I just did. Some of them are going to be rectangles using Riemann sums. And with that, we'll be able to approximate pretty accurately what the definite integral is. So I can't figure this out yet, but in subsequent videos, we'll be definitely finding an estimate for it.